Mechanical vibrations, we're just going to do an introduction with this, and you'll see this in a few other classes, but we're looking at movements that are going to suck energy away from the system, cause fatigue, failure, all kinds of stuff that's very important to understand vibrational motion. To get started, we're going to go back to a weight on a spring. This is from like chapter 11 stuff, and spring oscillation motion is kind of the essence of mechanical vibrations. In fact, finite element analysis that's used to look at stresses in materials connects elements together with springs. So it all actually comes down to this very simple force equals K delta X scenario. Okay, so what we have is initially you have an unstretched spring. We're actually going to stretch it out and call the equilibrium position. This is where we're going to measure our displacement around, and I'll show you why in just a second. So every problem is going to start with a free body diagram. A free body diagram of the forces acting on this block. We have the tension from the spring acting up and our weight acting straight down. And if we're in equilibrium, these two forces are equal and opposite to one another. So in this starting position, our K times that stretch of the spring, this is just how much the spring is stretched out, is going to be equal to W. Okay, so what happens if we stretch it away from that equilibrium position? So now our tension is larger than our weight force. And of course, the difference in these forces here is what causes the acceleration, the motion. So let's just write a couple of equations here. Again, we're going to call X the distance that it's stretched out, not from the unstretched spring, but from the equilibrium position. This allows us to break up that spring force into how much of it is from the equilibrium and how much of it was equal to the weight. Okay, so we're doing this to get rid of the weight here. Okay, so remember in equilibrium, these guys were equal and opposite, so we get rid of it, and this just simplifies our equation if X is measured from the equilibrium position. So now we have the force from the spring, Kx, is equal to how fast our block is actually moving around. And remember that acceleration, that's the second derivative with respect to time of our position. So here is our equation. We've got second derivative of x versus x. This is a little bit of a differential equation, but not too bad to solve. There's a couple different solutions for this. And it's going to be either a sine or a cosine. So remember, when you take the derivatives of these guys, sine, cosine, sine, they turn into one another. So you can get this equation to add to 0. So that's, I know it's differential equations, but it's not too difficult. And what you end up with is a sine and a cosine wave. So you get that oscillating wave that has a frequency and a period, and we'll go through kind of, hopefully you've seen a little bit of this before in maybe a calculus class or a physics class, but it all comes from just force equals Kx. It's just a simple spring with a weight. Just a couple of definitions here. When we say mechanical vibration, we are just looking at some sort of oscillation, and this is going to be defined from a position of equilibrium. So right in the center here, that's where forces going up are equal to opposite to the forces going down, and it's going to be just going up and down around this equilibrium point. And yeah, usually vibrations are no good, and you have to worry about balancing your system and energy losses associated with them. Okay, if you remember from sine and cosine waves, the period of vibration, that's how long it takes for one cycle to happen. So if you have position on the y-axis, time on the x-axis, and you look at how long it takes before the cycle starts repeating itself again, that time is the period. Frequency is cycles per second or hertz, and frequency is the inverse of the period. So 1 divided by that time, that's 1 cycle for some amount of time. So frequency is just the inverse of the period. The amplitude, that is how tall your wave is. So how much it's moving from that equilibrium position. Free versus forced vibration. If this motion is happening because you're pushing on it with a motor or something, that would be forced. Versus free vibration, if, yeah, like the weight on a spring that you just let it go and it is going all on its own without anything pushing on it, that would be a free vibration. And damped versus undamped, this is kind of, so usually these vibrations will peter out to 0 eventually because of frictional losses and heat and all of the non-ideal situations, and you can put in some damping into that sine and cosine wave to force it to 0 after some time period if you want. Here's a close-up showing the period of the wave. So the period is just the time it takes for it to come back to that original position. You can measure it from crest to crest or from where it crosses 0, just so long as you're coming back to that same position again. And the frequency is cycles per second, which is 1 divided by the period. So T is period, F is frequency in hertz. Okay, so how does amplitude, frequency, period, all of these things map out when you're looking at an equation of a wave? So here's an example equation. We have the position of some object is equal to 10 times sine 3t. So if you saw this equation and you were asked, what is the amplitude? What's the frequency? What's the period of an object that is described by this equation? What would that be? Well, let's do the amplitude first. Of course, sine, this chunk of it's gonna go between 0 and 1, and whatever is multiplied out here at the front of it, that will be the amplitude of the thing, okay? So the amplitude is just this 10 in front of our sine wave. How about the period and the frequency? That's going to get into what's happening here. Now we're going to assume that everything is happening in radians, not degrees. And to think about the frequency, let's look at some units here. Okay, if we look at the angular velocity, this is radians per second, and we don't actually want radians for the period and frequency. We're looking at what's happening for an entire cycle. So an entire cycle happens over 2 pi radians, and all we have to do to go from radians per second to the frequency or the period is just to multiply or divide by 2 pi. So what we have is our angular velocity, which is this 3 here. That is equal to either 2 pi over our period, or we can say omega is equal to 2 pi f, where f is our frequency. So again, all we're doing here is it's a units thing. So we're going from radians per second and trying to get cycles per second out of it. So just a little bit different. So you can solve for the period or you can solve for your frequency. Okay, so, and these two are just inverse of one another. So 1 over your period is equal to your frequency. So seconds per cycle or cycles per second. Either way, it's the same sort of thing. Simple harmonic motion. Coming back to this equation again, so force is equal to ma. And we have this set up so that the weight and part of that stretch cancel out. So we're measuring it with respect to that equilibrium position, second derivative with respect to time, and our position. Solving this differential equation, we get a solution with sines and cosines where the natural frequency of this thing is dependent on, this is just the spring force, the spring constant, sorry, and the mass of our object on here. In order to figure out what these constants are, let's go ahead and take, so we have the position is sine and cosine, take the derivative of position, you get velocity. So sine goes to cosine goes to sine. And we're going to plug in our initial conditions. So initial conditions, time equals 0. Sine of 0 is 0, so we're left at cosine of 0 is 1. So C2 is equal to just our initial stretch of how far down we've pulled it from that equilibrium position. And over here, so sine of 0 goes to 0, and we have cosine of 0 is 1. And our C1 is going to be related to our initial velocity that we let it go with. Further simplifying this equation, what we can do is just wrap everything together into just a single sine function that has the natural frequency and a phase angle. The amplitude is going to be a function of our initial velocity that you started with and just how far out you initially stretch the spring. So there's your amplitude. And again, the phase, so just depending on what position along this curve you're calling time equals 0, so you can shift this one way or the other by just adding a little phase angle into this. And our period, this is going to be the inverse. We're going from radians per second to time per cycle. So 2 pi radians per cycle, and just watch your units on that to go between period and frequency. So frequency is just the inverse of the period, and radians versus cycles, you're just throwing some 2 pi's in there. Okay, so here is position. Take the derivative of position and you get velocity. Derivative of velocity, you get acceleration. Going from position to velocity to acceleration, this is back to chapter 11 stuff. So just a little bit of calculus to go from one to the other. So remember all those relationships, that when is your velocity a maximum? When is your acceleration a maximum? And how are these three graphs of position versus time, velocity versus time, acceleration versus time, how are those three graphs and entities related to one another? Here, I'm going to just throw these into Mathematica and look at these graphs. So let's say here's our position as a function of time, has some kind of an amplitude, our frequency, and our phase. So we have position going to velocity, going to acceleration. And if we graph all these out, what are they going to look like? Remember that when position is a max or a min, it's going to stop before it turns itself around. So our velocity goes to 0 when our amplitude is a max. And if we want to figure out where acceleration is a max, that's going to happen when the spring is all the way stretched to its maximum amplitude, right? So position and acceleration are mirror images of one another. And the velocity, the 0 velocity, is going to happen when our acceleration is a max. So hopefully you can start remembering some of the relationships between position, velocity, and acceleration. Back, we've come all the way full circle to chapter 11 again. So let's go through just an example. What is the max velocity? If we have some equation for the position as a function of time and we want to figure out when our velocity is a maximum, and it really does help to graph these functions out so you can see what is happening as a function of time. So where's our velocity? A max. So we're looking for where the orange curve has the largest amplitude, and you can see the max velocity happens when acceleration and position are going through that equilibrium point. So velocity is a max. It's not speeding up. It's not slowing down. Acceleration is 0. The max velocity happens when it's zipping through that middle position, the equilibrium position. So if we just set x equals to 0 or a equals to 0 and find what time this happens at, plug that time into our velocity, and we can find when velocity hits a max. So here we go. So we say solve when does our position go through 0? And then we can take that time, plug the time into our velocity equation, and find what our maximum velocity is. How about acceleration? When is acceleration a max? So again, look at where the green curve here, this is the second derivative, this is our acceleration. Where does this max value happen? If we come up here, acceleration is max when velocity is 0. So the velocity slows to 0 when our amplitude is at a max. So you've stretched it all the way to the top or stretched it all the way to the bottom. Our position is maxed out. That's where the spring is stretched out the most. That's where our acceleration is stretched out the most. And the velocity stops. That's a turnaround point. When it's all the way stretched out, it stops before it changes direction and comes back the other way. Okay, so acceleration is a max where velocity is 0. So all we have to do is find what time is our velocity equal to 0. So if we plug in and say, what time is our velocity equal to 0? We can take that time, plug it into our acceleration equation, and find out what our maximum acceleration is. In summary, if you have this generic equation for position that's some function of sine with your frequency and amplitude and phase change, the general solution is your maximum velocity will be equal to amplitude times your frequency, and then the acceleration, the maximum acceleration, is going to happen where your amplitude and omega squared. So these are general solutions if you have some equation of position with sine in it. Here's an interesting example problem showing how springs add together in series and in parallel. What we have here, a 20 kilogram block moves between vertical guides as shown. The block is pulled. So here's the initial displacement and released from rest. For each spring arrangement, determine the period, the maximum velocity, and the maximum accelerations of the block. What we're going to do first is we're going to find an equivalent spring. So if these two were combined into just one spring that would give the same equivalent force, what would that single spring look like? And we'll do that by just drawing a free body diagram of our block and looking at how these forces add together. We're then going to apply the general solutions that we had in the previous slide using our equivalent spring constant instead of the individual spring constant. Here is the first case where we have our two springs are parallel to one another. If we draw a free body diagram of our block, so we have the weight of the block acting down. Each of these springs in this case undergoes the same displacement. So I can take this displacement, so how much each of those springs is stretched out, pull it over here underneath my force, and our equivalent spring constant is just going to be each of the individuals added together. So K1 plus K2 is equal to an equivalent spring constant, and then it's like we have a block with only one spring acting on it, and we can use the general form of all those equations that we had before. Okay, so here is our radians per second, our frequency, and we're just, instead of using individual spring constants, we're plugging in this equivalent spring constant into our equation. So here's the period. Again, we're just going from radians to cycles, so we're going to use 2 pi. Here's our maximum velocity and maximum acceleration. So we can use all of those general forms if we just find the equivalent spring force. How about springs that are added in series? In this case, each spring undergoes a different stretch. So how much one stretches out is different than the other. So we're going to have to add these together a little bit different. Okay, so the load is equal to the equivalent spring constant times the overall distance, which is d1 plus d2. Okay, so we take this overall distance, d1 plus d2, and each of these stretches is created by just force equals kx, or x equals force over k. So we have the load over k. We're just looking at the stretch. The stretch is produced by the load divided by the spring constant. And so we kind of have this inverse addition for our overall displacement. Okay, so our overall spring force, K equals force divided by displacement. Force divided by displacement is equal to this guy over here. Okay, so it adds together a little bit differently here. But we can, again, get an equivalent spring force. And once we have that equivalent spring force, we plug it into the general form of those equations for our frequencies and periods and max velocity and max accelerations. You just have to walk through solving for that spring constant again. Here's a summary looking at how those springs add. So springs in parallel, you just add K1 plus K2 because they both deform the same amount. For springs added in series, this is the equation to find the equivalent spring constant. And it's opposite for adding resistors together in circuits. So if you remember how to add resistors in circuits, it looks a little bit similar, but it's reversed. One more extension talking about oscillating motion. Let's look at a pendulum. So we have a mass on a string of length L. If we draw a free body diagram of this mass, we have tension. Let's go ahead and define our coordinate system in the normal and tangential directions. And we can split our weight into how much of our weight is held up by the tension and how much of our weight is not balanced and would create acceleration. So here's the angle that the weight makes with what the tension is doing. And W cosine theta, that's what the tension would be. W sine theta, this is the unbalanced portion of the force that would create motion. So here's another sine equation. Whenever you see a sine wave, this is going to be the same types of solution that you saw with the spring equation. Okay, so here we have the tangential piece of the force, and this is a part of the force that's not balanced. It does not add to zero. It adds to how fast the thing is accelerating. And that unbalanced force involves sine. The acceleration, remember angular acceleration equals r alpha. R in this case is the length of our string, and alpha, that's the second derivative of, so this L times alpha, that's our acceleration, how it's moving around. Now this is a little bit trickier of an equation. We have theta inside of that sine, and so I don't want to go into some huge differential equation thing. There's a little bit of a fudge factor. If the angle is super small, then sine theta looks the same as theta. They're very similar to one another. And this is an easy equation to solve. Okay, so this you can go back and figure out your omega and your phase and your period and everything. If that angle gets larger, it gets a little bit messier to solve, but again, it's a sine theta relationship. This is what most people use. So instead of going through and actually solving this rather ugly situation, there's tables that are created for this. And so you can just look up correction factors in your table for this case rather than trying to walk through differential equations to solve these things. Okay, so anything that starts in this form, whether you're looking at positions or angles, we're going to end up with some kind of sine or cosine solution that creates simple harmonic motion. One last case to look at here, let's say instead of just a single pendulum with a ball at the end of a string, we have some kind of a two-dimensional, three-dimensional object that is bouncing around with this harmonic motion. The only difference with this guy, again, we're going to use this solution where sine theta, we'll just look at small vibrations, so very small angles. And if you're dealing with a two or three-dimensional system, the big difference here is you're going to have to add in that moment of inertia. So our acceleration is going to be kind of twofold, where you're looking at the inertia of whatever shape it is. And you can look this up in the table. So for a square, it's 1/12 m, 2b squared. So just look the inertia up in the tables, and you can plug that in and find your accelerations and your frequencies. Okay, so there's a bunch of examples in the notes. Let me know if you need to see more examples. If you find some other really good YouTube videos, please post those for D2L points. And that is the end of this book.